Hi, welcome to Short Circuit IoT Development with Nerves. Today we're going to be talking about a framework in the Elixir programming language called Nerves, and we're going to be looking at some development patterns. So I had a little bit of the development story of how this talk began. It originally began as a sort of telling of how I built or worked on a solar microgrid. And eventually it wound up being a little bit more about development patterns. Yeah, let's go. So a little bit about me. If you want to follow me on social or on GitHub, which I do also consider a social media in some regards platform, these are my handles. A little bit about me. I'm a senior software engineer at Very. Very is an IoT consultancy. So Internet of Things projects are our bread and butter. If at the end of the talk you don't have any other questions, you can always ask me about prog rock, my dog Bowie, or renewable energy. So for this project, I was very fortunate that I got to work with Daniel Spofford and Justin Schneck. If you ever get a chance to, working with them is like being strapped to a rocket. So yeah, highly recommended. When thinking about writing this, I also have to take into mind what I think about you. So at first, like I said, this was a pretty advanced talk, and I wanted to dive very far into the weeds, and we do. But as I went on, it's primarily about development patterns. So whether you're new to Elixir, or whether you think you're just a web dev, or if you think that assembly is made for developer happiness, this talk is for you. So if you're at Open Source Firmware Conf, I also think that you have an interest in IoT projects. And maybe if you read the talk description, you realized it was about solar and renewables. So maybe you like sunbeams. If that's you, you're in the right place. So from a 1,000-foot view or 10,000-foot view, Nerves is a way to compose build root Linux systems. So it's embedded Linux. It's not RTOS or any other kind of lower things than that. It is built on build root Linux, and it will boot you into an Elixir shell. And it has a lot of commodity targets, but you can also target novel hardware, which we did for this project. So I guess most people probably would identify as on this left column here as full stack. So front end, back end operations. At Very, we have a joke about IoT just being the fuller stack. So we basically take full stack and then we kind of like stretch it out to include mobile apps, machine learning pipelines, but also firmware and hardware. So this is going to focus primarily on those bottom three that I've circled in here. And if you're a full stack developer, a good habit for you to be in is to be conversant with your neighbors. Well, what do I mean by conversant with your neighbors? What I mean is, if you are a backend developer, right, your application will take in configuration and change itself slightly for different environments. So say you have stage and production, right? You'll read from envvars possibly, and you might make some slight modifications to its behavior. So that's your backend being ops aware and knowing kind of what's going on around it, especially if you're following the 12-factor app. Your operations will have a direct impact on your backend systems. Or like if you're a front-end developer, not to make a million requests to the backend because that would, DDoS your own system. And so that's you in the front end being conversant and saying, hey, I know I need to just ask for what I need and nothing more. And then lastly, if you're in operations, you understand that you might build log aggregates for your front end, back end teams to kind of observe their systems a little bit better. I think it'd be too much to cover everything in this stack. So we're going to focus on how to talk to hardware and how to talk and think about firmware. So the two primary directions that we're going to go in are we're going to look at, I'll be sharing experiences from building that solar microgrid controller. This is only one of the parts of that project, but I just felt like it was really ripe to talk about. So first we'll look at things you'll get wrong and some of the assumptions that you make in order to get them wrong. But I'll challenge you that you either don't need to make those assumptions or that you don't normally make them, so stop making them here. And then we'll look at how hardware is similar to developing software. So every project that we build in Nerves starts with typing mix nerves new and then naming it. So let's kind of like take a look at what that is like. So as soon as you start a new project, you're going to run into your first problem, right? Especially if you're new to firmware. This is a script that kind of goes, well, I hear it a lot. At least I hear it a lot because it's in my head when I was transitioning from web dev to firmware developer. Hello world is all different. I don't remember how to read a resistor, which direction it goes. Is it orange, brown, gold? I don't know. And you're confused about the LED, and you're thinking like, oh my god, this is not for me. This is stupid. I need to go back to web dev. The problem you're really saying here is you either don't have hardware or you're worried too much about it. So what does me telling you don't worry about hardware have to do with how you're going to build out your solar microgrid controller? Well, when learning to speak a new language, and in this case, we're learning how to speak to firmware and learning how to speak to hardware, we need like little wins. So let's go ahead and grab ourselves one. So the problem you're making, the assumption that you're making, the thing you're getting wrong, is what I call the for versus on assumption. So that means that people think if I develop for a Raspberry Pi, then I need to develop on a Raspberry Pi. And that will certainly become true. You will eventually deploy this to some target somewhere, but it's not helpful when you're developing the application. So if you're coming from web dev world, this one's really easy to translate. So just because I develop for prod doesn't mean I develop on prod, or at least not all the time anyway. So if you're an Elixir developer, IEX is the way you're going to run an interactive shell, and smix is going to start your project. So if you're familiar with running this is running just any Elixir software locally. When we were developing the solar microgrid, I would say the majority of development was done in a fashion similar to this on our Macs and not on whatever novel hardware we chose. So just in case you don't believe me, this is an example of an application that I wrote called Weatherball. I'm from Grand Rapids, Michigan, and we have a thing called a Weatherball. It's got different statuses and different colors based on what the weather is going to be. It's pretty silly. But this is pretty similar to what a hello world would look like. And you'll notice that I'm running it from my machine. There's no Raspberry Pi, there's no BeagleBone, there's no nothing. I don't have any LEDs set up, but I'm able to start iterating, and I've pretty much got all of the business logic for a Weatherball app anyways complete, and I don't have any hardware for this application. So I'm mostly staying in business logic land, which is really where you want to be. So it's a small win. So functionally, what that's doing for you, though, is changing your problem statement into a solution statement. And even as you move past hello worlds, this skill is still incredibly applicable. So when we are, building out a firmware project, we're also taking into consideration what new hardware we might need. So our electrical engineers, they'll consider, what are some lower cost non-commodity versions of hardware to build on. And while they do that, our software engineers, our firmware developers, can still work on application logic. And so you don't have a problem of I don't have hardware right now. You have a solution, which is I don't need hardware to develop the application software that this thing is going to produce value for. And the majority of that is not hardware integrations. The most of the time you spend on firmware projects is not on developing directly against the hardware. It's pretty much kind of like web dev, where you only kind of do your database connections once-ish, and your startup logic maybe once-ish. Maybe you revisit it again when you learn something new. But disappointingly, firmware isn't very different, right? You want to spend your land, again, writing business logic. So the main thrust here is that this is going to cut down iteration time, because if you're trying to push your firmware to your hardware all the time and test on the device itself, you're going to find yourself operating in iterations in the order of minutes, maybe. And that's a lot slower than how fast our tests run, which might be on the order of seconds. So some of the things that we learned while developing the microgrid, right, is that eventually you do get your hardware, your resistors and everything up and ready to go. And the patterns and tools that we use to develop for that are going to seem very, very familiar. So if you're an Elixir developer, there's a library called mocks. And mocks is usually used for mocking out modules and functions for tests. And it's really useful because you don't want to actually test against the database or things like that. So at Very, we developed a module called Hook, which allows us to dynamically dispatch the appropriate module to our running software. So let's say we want to start actually talking to a GPIO. Mox gives us a way to inject an appropriate module at runtime, but still allow us to build the software without making too many extra hoops and runs around it. So if you know kind of like dependency injection frameworks like Spring, that should be pretty familiar. But the other thing that it allows us to do is create a hardware abstraction layer, or a HAL. You might see it around in some of in the future slides. Again, basically, it's just allowing us to make a stub for running locally that behaves exactly like the hardware will in real life. And I like really some of the modules out there. There's a Circuits GPIO. I want to give them a shout out because they have put a stub implementation like the top of their README. And I think that's a really, really cool practice. The next lesson that we learned, other than developing Hook, was to really leverage, abuse, and use the configuration EXS. So if you're not from Elixir land, this allows you to set a couple of different environments and kind of alter the configuration based on this thing called, or based on different environments. So we use mixed target to say whether I'm targeting my host or maybe I'm targeting a Raspberry Pi or a BeagleBone or something like that. And so it's very similar to how you might run a stage version of an API versus the prod version of an API. It might reach out for slightly different configuration, but it'll still be making the same calls and making sure you're exercising your business logic and making sure you're exercising your application in the usual and expected way. So yeah, in firmware, instead of having the mocked out things, we have this HAL, right? And so you can see CPU.ex, the top level ones, disk.ex, memory.ex, and network. Those are the modules that are responsible for the business logic. And then inside of these subdirectories, those are the ones that are responsible for the implementation logic. So we can stay kind of still developing and keeping our iteration cycles really, really short. So if we want to look at how Hook is used, it is macro expansion, which might not be super meaningful to you, but this is kind of what it looks like in practice. We use Hook, and the only function here right at the end, hook archive insert, is saying, hey, Hook, go ahead and give me the right archive module and use its insert function. So this allows us to build out that hardware abstraction layer, and we hook those mappings into that configuration file. Speaking of config, so we're going to use that to get different modules for the host and the target, and they're going to behave very, very similarly. So this is the directory of a system info module that we created. So we needed to know about the CPU util, the disk util, memory, and network. And so, this would allow us to get some metrics about our running firmware. We can make some important choices about that, which we'll talk about in a second. But even for these two things, even the difference between, for example, disk utilization, it's useful to have this for example, a Raspberry Pi and a Mac, because Getting disk util is very similar, but it's slightly different. So you can change those implementations and find the right target. So just to recap, I'm insisting that you develop locally to speed up iteration time. And I want you to abstract the hardware layer as soon as is feasible. And think back to the system info module we just talked about. Why in the world might we care about something like that? Well, our next thing to get wrong is going to tell you why we care about this information. It'll help us solve one or two problems. So those problems, I want to talk a little bit about the application that we developed. So it was a solar microgrid controller. What does that mean? Well, there are many solar panels collecting collecting photons and generating energy, right? But they're also hooked up to a meter, and the meter is saying, how much energy are you producing? How much energy are you spending? And this information is being sent to the project we did, the controller, and it's sending all of this utilization information because the person who runs a microgrid controller is acting as a utility company, in most cases. So in the deployments, these are put in places where you don't get a traditional power grid. So it'd be remote locations in Africa or Canada or Australia, where you see the 8 fallacies of distributed computing. Things like I might not have internet, maybe for a couple of weeks, and somebody might have to bring it in on a backpack, and it's going to be satellite. It's not going to be very fast. Or you run into things like, I'm going to run out of storage space, but I have to store all of this meter usage data. In many cases, because they're so far away, we have to hold on to this information. But we're sort of on a ticking clock of when am I going to get to the internet next? Because I've got to get this data up to the cloud and let people know, whether they were being charged for energy usage or making money by creating energy. So if you're new to firmware, you might think that because you're developing on a constrained environment that you are somehow constrained. And these definitely seem like constraints, right? I don't have access to the internet, so I can't get rid of this data, but I have to hold on to it. So the way that we were able to at least have metrics to make business logic was by using Linux. So remember I said NERVs is build root Linux at the end of the day. You can kind of piece together and build modularly the dependencies that you need. So the way that we got this information was, we were going to use df, and we were going to look at procnet stat, and we were going to be able to figure out this information pretty much just like you would on a desktop Linux machine. And I think that's kind of like a little bit of a let the air out of the balloon disappointment. But to me, it really isn't. If I can use tools that I'm already familiar with, that's going to speed me up. So during this project, we did build out an additional little module in Rust called a port to actually talk to the meters. And we also experimented around with like bmon and vnstat for more advanced network utilization statistics. But we ultimately wound up thinking, well, those are nice, but we had to rebuild build root and add in those dependencies. So we went ahead with, do the very simple thing, which was, use Linux. Plus side is if you ever find a utility and you don't have it available, you can add it back in build root, so you can rebuild your NERVs target and get the thing that you do need. Let's say you did actually need bmon. The process is, available to you to do that. It'd be a little bit like if you've ever worked on an Alpine Linux Docker container and you forgot that curl wasn't there. You just kind of go through an iteration cycle like that and then get your, build root Linux system up and rolling. Cool. So when I say like we used Linux, I mean, these are the actual honest to goodness implementations of getting the network utilization or the disk utilization. And if you're thinking to yourself, well, it just looks like you're reading files and doing regex. I totally agree with you. Couldn't agree more. That's exactly what we're doing. So just like when we write JSON, we parse the input and we save files to S3. In firmware land, it's all pretty much the same, but just a little bit different and smaller. The main difference here that I want to call out is how aware of being on a computer you should be. So it's not so much a constraint, it's just understanding that you are on a computer. In AWS land, we can just make the EC2 instance bigger, add another X gigs of RAM to something. But on embedded systems, we don't have that same, we can't just download more RAM to the Pi. And because we can be aware of our impact on the system, we can use this information to decide when it's appropriate to send a message. Hey, how good is the network connection? Hey, am I running out of space in my database? Do I need to run some compaction algorithms? Do I need to run some more compression? So I really wish the answer was cooler than like use Linux and develop local, but it kind of isn't. But I also think that that's going to be the way that you're going to do the fastest and best development that you can. So all the things that you would get wrong if you weren't developing firmware, if you're doing web dev, are the same things you'd get wrong if you were developing firmware. So keep your iteration cycles tight by developing locally. Use the tools that are available to you. Use stock standard Linux. Don't get fancy unless you have to. So best practices for firmware development are just software development practices in disguise. So far in our journey to become conversant with hardware, we found that you're only as concerned as you think you are, right? Stand on the shoulders of Linux whenever possible. And you don't always have to talk to hardware. In fact, you don't want to talk to hardware, and it's probably going to slow you down if you get hung up on talking to it. So we've discovered we already know how to get around these things that we get wrong, but we're introducing hardware into the mix because my Pi just showed up from Amazon, and here we go. So a little bit of a sidetrack. A while ago, I built the Dan Lindeman public library, and I built it using Flask and MFRC, which is an RFID reader. RFID readers are ways to store information about, a lot of you probably use key cards, or a lot of you maybe went to the Fire Festival. That's that technology. And I wanted to make my own public library system because I buy books, but then I lend them out to everybody, and it's really hard to keep track of who's got my stinking books. And I talked about this at several Python conferences. So in that one, I used Flask, which is a web development framework in Python. I used MFRC 522 Python, and I noted then that I was like trying to work on, I wanted to work on an Elixir project, but I didn't know if my hardware would work together. So I used Python because I'm still a little bit faster with Python than I am with Elixir. But I did note in that talk that I was pretty disappointed with the coordination between this RFID reader and the Flask web app. The reason I was disappointed with it was that Python either doesn't make obvious or makes difficult developing firmware. So it has a notorious problem of being a single locked interpreter. So GIL is there, and message passing between the two services. I was thinking about maybe implementing Redis or some other, an additional HTTP server and running them all in their own different processes. Well, if that's the case, how do you really structure the application? Well, it turns out in nerves, in an Elixir land, processes, it's not Linux processes, but it is Elixir processes, are a really, really good idea. They're essentially their own space with their own allocations of memory, and they're under a supervision tree. So they're a really, really useful way. Instead of launching a bunch of different disparate software projects, a web app, and something that's monitoring an RFID, and launching Redis and having things communicate over them, in Nerves and in Elixir, you kind of get those for free. So let's revisit the RFID application. The real problem I had there was that Flask holds you in a while true loop in some sense. Same with MFRC 522. In this case, there's a literal while true inside of the code base, And so basically you have two while loops that need to coordinate with each other. And the problem was sharing. And so essentially I chose a really hacky way around it. I would just stop Flask for a little bit and then occasionally stop the MFRC, the RFID reader. And so basically I just forced them each to kind of quit or reboot, not reboot, but to break out of their loop for a moment and allow the other one to kind of, keep a running Flask application while also still scanning for RFID tags. And again, I suppose like the right way to do it would be to use maybe coroutines or like Redis or something, but it was kind of a pain. So in Nerves and in Elixir, I can use processes. So Phoenix is also a web framework in Elixir. And if I run that, it runs in its own process, which means it's run as usual, as expected. Whereas Flask is in a while loop and it's holding the entire, interpreter. I can also use Circuits SPI and craft something called a gen server, which is basically a process that can be kept alive with a piece of state. And that can read from SPI and read that RFID tag. And that's contrasting to MFRC Python, which is, again, a while loop that I had to kind of break back and forth. So we're seeing here that Phoenix is run as usual. Circuits is run as usual. They're also being supervised by the same application. And the way that I'm able to coordinate between the two is by using Elixir message passing. And so these processes can discover one another and communicate with each other. So I have built them all in a single application, but I don't have to make any exceptions or change the architecture of my firmware, right, to make up for lackings in the language or in the runtime. And so this also scales with multiple services. These are just two examples. So in the Solar microgrid controller, I tell you all of that to tell you this. This is really how we did it in real life. Phoenix was our admin application, so the user could change settings on the device or do a software reset or kind of look at some of the information on the controller at present. We use Circuits SPI, or rather we use Circuits GPIO for reset button and tamper detection. So like an actual boop boop, reset the firmware. I did tell you earlier that to talk to the solar meters, we had to build a port and we threw that into a gen server. All of these have their own process. All of these are supervised by our application. And we can know that if they crash, we can bring them back up. So they're very fault tolerant. They're very fast to develop. And with the patterns we talked about earlier, leveraging Linux and developing locally, we were able to build this application in a much shorter time span and have a lot less complicated of infrastructure or application architecture. So in sum, leverage your hardware abstraction layer in business logic processes. And also, if you're using Nerves, be grateful for message passing in processes. It's a really solid model for building firmware. And it's a really good way to make sure that resources have access to their, that processes have access to their resources and don't have to fight with each other. So we're really moving. So I want to look at our next problem here. So the next problem when you're developing your, a novel piece of hardware. So I've talked a lot about BeagleBones and Raspberry Pis. That's all in service of, while our electrical engineers, they're working on a custom board. And we'll use, a different Wi-Fi module or a different USB module than the ones that are on the Pi or the BeagleBone. But because we've already been building in a hardware abstraction layer, once we can get the hardware in, we'll start running into this problem, which is we think that hardware specs are very accurate and super helpful. When I first got into software, I was a manual tester, and I think that some old wise sage said this, and I can't tell you how resonant it is. It's probably one of the only few truths that I find in engineering. So the same way that hardware is software, software docs, they're not always the best. And we know that in the software world. And of course we should know this. If you think about even what hardware and software is, right? Hardware is a retronym. So hardware used to just be called, whatever the thing was, a calculator or a loom. It wasn't until we got software that we renamed hardware, right, to be hardware. So if software docs lie, it makes sense that our forebear, hardware, their docs would also lie. So how do we get around that in regular development? We get around that by, you don't learn a programming language by reading about the compiler. You write hello world. You get a feel for the language. You just write a smaller application. You write several hello worlds. You also write tests around any new libraries that you're pulling in. So let's kind of update that. Quote. It's not just software documentation. It's all documentation. So what kind of lies can we expect to see in hardware? Well, if we're translating, one-to-one, tolerances might be like API request limits. There could also be, like max page size would be something that would come up in web dev, but all of a sudden, it's, well, which endianness is it? All sorts of things that you need to think about. So the way you should think about this is every time you add a new piece of hardware, so Ethernet, Wi-Fi, or whatever, think about it the same way you would if you were adding, a new HTTP library to your software application. So what you would do is you would try some stuff out with it. You'd get a good feel for it. You would write a hello world, and you'd write some tests to make sure that you really understand how it's working. So how are we going to do that with hardware, though? We can't we can kind of just swap things in and out, but what's the best way to do that? And I would implore you to think about each piece of hardware as a new software dependency. So what happens if you ignore each new library and ignore running spikes and running hello worlds on each component one at a time is you'll eventually get to the big bang where you've added a bunch of different hardware components together and you believe that they're just going to work. And so that's the huge problem, which is, you have all of these things that you didn't know whether they would or could integrate. And all of a sudden you're trying to say, okay, well, they all should work together. But each one is going to have different tolerances, is going to need little new interfaces, is going to need a slight adjustment to work in symphony with everybody else, just like your software dependencies. So in software, we can write patches, we can write adapters, and we can force things to play nicely together. In hardware, we can also do patching. And in fact, patching is a hardware terminology, as many of you are probably already chuckling to yourselves and familiar with, right? But it's just the order of patching hardware is on the order of maybe minutes or hours, and the order of patching software is on seconds. So when you're thinking about how to deliver value quickly and short circuit your IoT development time, what we do, at Very is try to keep into that really, really tight loop. So what are the ways that you could do that? Well, we have our hardware components, right? And we're able to print out boards using a very expensive machine. Because the hardware has, different tolerances, or it has some sort of limitation to actually being integrated into your system. So we, in order to avoid the big bang, print out our components and dependencies kind of one at a time and add them very modularly. It's the same practice you would do in software development, which is just add one dependency, don't add 40 things and assume they play nicely together. We basically build out the smallest possible hardware and the smallest possible software, and then we iron out those kinks and say, okay, what patching do we need to do? What adapters do we need to do? So basically, if you're thinking about this in terms of software terms, we use test-driven development, and we do spikes, aka hello world. In our journey, it might be some time before you can buy PCB printers, but even with breadboard and a soldering gun, this pattern still applies. So take your time, add one dependency at a time, just like you would in software. So I hope I've got you some tools for thinking about firmware and hardware. I hope you feel inspired by how few barriers there have to be in order to start getting firmware done and getting firmware done right. If you are interested in Elixir or even Erlang, you will happen to know a language that makes these things very obvious and a lot easier. So I encourage you to use it if it's not already part of your tech stack. But again, we found that I wanted you all to walk away feeling like Freddie here, which was like, well, I didn't really tell you anything new here. I told you to use Linux, to develop locally, to write tests, and it's basically software development best practices. But you might not have known that they were applied there. So if any of this sounded cool, again, reach out to me on Twitter or follow some of the stuff that Very is doing on GitHub. We're also hiring. So if you want to work with folks like myself and work on projects like this, go ahead and find us. Thank you so much for your time. I know we all only get so much time and attention per day, so I can't tell you how much it means to me that you've spent some of yours with me.